we are going to talk actually mostly about the kinetic theory of gases and then get into the mechanisms of heating. So this picture will come up again for mechanisms of heating. I've already talked about this slide enough. I was going to delete it and didn't. So let's get right into the kinetic theory of gases. Now, I've had students complain about the content of this lecture that is going through the kinetic theory of gases in the past. Like, it's all so theoretical. So I'm telling you right off the bat why I am doing this. I have told you since the first time I mentioned temperature that temperature is a measurement proportional to what microscopic value? Okay. I know I put that in the form of a whiplash question, but you answer. What did you say?
No, I was trying to understand.
Oh, she's trying to understand the question because I put it in the form of a whiplash question. For those of you who take your education classes and my education classes, they said don't ask questions where it starts sounding like a statement and then it ends with a question. Because the students start in a receiving mode, so to speak, and then all of a sudden, wait, I'm supposed to actually be thinking? So what does temperature measure? Something proportional to the average kinetic energy. So I told you that, but being told that, it should be highly unfulfilling. Because just being told something is like when you're a kid. Richard, don't put your hand on the stove. Why? Dad does not stick my hand on the stove. See, I told you not to. But he explains it will hurt you, blah, 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 and shows me some kind of example, like, see, it started this paper on fire. This here is to show you why temperature is a measurement that tells us about kinetic energy. So the kinetic theory of gases is connecting the motion of atoms to what pressure and volume measure and getting us temperature. So we start with, let's imagine that we have a box and we have a particle bouncing in the box. So this picture here, we have a particle that comes and hits the wall and bounces off. When it bounces off, it's going to change momentum. In what direction is it going to change momentum? Let's say, to make life easy, let's say the wall is this screen. So a particle comes in, hits the screen like this, and bounces off. What direction is it going to come off? It's going to come off like this. Its momentum in the direction normal to the screen will have changed because there is a force normal when it hits the screen. Assuming no friction type things, its momentum in the other directions won't change. So its momentum is only going to change in one direction, the direction opposite to the force normal. And we know that the net force is change in momentum divided by change in time. Now this is a vector equation, of course, so I'll put my vector signs. That is going to be our starting point for doing this problem. There's going to be a force applied to a particle every time it hits the wall. And we know that pressure relates to that force because pressure is force over area. So we're going to build up from that. Here we have X, Y, and Z directions defined for this wall. So in which direction did the momentum change when it hit the wall? With these definitions for directions right there. There's only three possible answers, X, Y, and Z. In which direction did the momentum change when it bounced off of that wall? Totally should have made this a clicker question, apparently. In the X direction. The X direction because that's the normal direction to the wall. Now, before I do this, let's look at some background information. An ideal gas, a diffuse gas, as we talked about the lecture before the review, doesn't perfectly exist, but we approximate it to situations where you have point-like particles, tiny particles with no volume. They have no interactions except for elastic collisions when they hit things. And that's going to include the wall. So this derivation I'm going to do is going to take that as a given, that it's an ideal gas. And for ideal gases, we've already seen through experimental work that you have the relation pressure times volume is equal to the number of molecules times a constant times temperature. So we already have that equation that we know that's going to come into this derivation. So we have a box filled with particles, and I'm just going to look at one particle, and then from that one particle take an average and determine what we have for all of them. So for one particle, when it hits the wall, its momentum is going to change. So one particle hitting the wall, now it's showing hitting this wall, opposite side wall as the previous one. And so the change in momentum is equal to, well, initially it hits the wall in this picture. So I'm going to go with what this picture is. We do change in momentum. It's the momentum final minus the momentum initial. And so the momentum final in this picture is going to be, in this picture here, in the minus x direction for the x component. The y and z components, you know what, I don't care because they're not going to change. So I'm going to have momentum final minus momentum initial equals, you start with momentum in the x direction going into the wall, so that's positive for the momentum in the x direction, comes out negative, your change is final minus initial. So in this case, it would be minus px in the x direction minus, and the initial was px in the x direction. Now, why do I have px in both cases, you may be wondering. If it's an elastic collision, the kinetic energy before has to equal the kinetic energy after, which means that the speed before has to equal the speed after, or the momentum before has to equal the momentum after. Since momentum in the y and z directions is remaining the same, unchanged, then the magnitude of the momentum in the x direction has to remain the same. All that can change is its direction. So if we have an elastic collision, you have to have the momentum magnitude in the x direction is the same. Its direction is just flipped from positive to negative. So the change in momentum is equal to 2 momentum in the x direction in the minus x hat direction. Now, I didn't give myself any more slides until we get to the end, so I'm going to go out sideways for the rest of this. Bad thing is, I went over this to prepare on Monday of last week, I think. So I have to make sure I do it all right. That's my change in momentum for each collision. Now, according to Newton's second law, the force net in the x direction is equal to change in momentum in the x direction over change in time. Right? That's taking Newton's second law, the net force is change in momentum over change in time, and applying it specifically to the x direction. Well, I've seen how much the momentum changes for a single collision. What's the time for that collision? Right, because that's the delta t. Easy answer, I don't know. I don't know what it is. But what I do know is the average time between collisions for this one particle. This one particle, if it has momentum px, then it's going to have Vx is equal to px over m, right? So I'm just going to work with that. Change in momentum is mass, change in velocity in the x direction. And instead of talking about during the collision, what's the force during the collision? I'm going to say, what's the average force caused by this particle on the wall? Because this particle, if it's in a box, it's going to come hit the wall, bounce around, come back, hit the wall, bounce around, come back, hit the wall. And so what I'm going to do is I'm going to say the force net in the x direction average is equal to mass well, I have to be a little more careful. It's going to be the change in velocity that occurs for one collision. What was the change in, I did the change in momentum here. The change in velocity in the x direction will thus be equal to velocity in the x direction. I dropped the minus sign because that only had to do with the direction. So now I'm talking about the x direction. I'm just looking at the magnitude. So the change in velocity for each collision is 2 times the velocity in the x direction. So for delta Vx, I'll put the change in velocity for each collision, and then I'm going to divide by the time between each collision. If I know Vx and I know the length of the box, I can get the time. Come back to looking at the box. The box has a length L. How far does the particle have to travel in the x direction to go from one side of the box to the other and back? 2L. I asked this question to make sure people were following along. So my distance is 2L. The time is going to be the speed over the distance. Speed over distance, that's not right. It's the distance over the speed. So it's going to be 2L divided by Vx is the time between collisions where the particle hits the wall. So the particle hits the wall, it bounces around in the box with a constant speed Vx until it hits the opposite wall, reverses to Vx this way, comes back and hits it. And so in the x direction, it's traveled the distance L, or 2L. The time is 2L over Vx, so question? Eric?
Why would it be 2L over Vx and not Vx over 2L? Would it be oh no, never mind. Yeah, I got it. Yeah, sorry.
Okay. So assuming I did not make any mistakes here, I know that, yeah, I wrote the wrong thing. I put over 2 instead of over L. I knew there was something wrong here. So the net force average, the average force that the wall is putting on my molecule over time is this mvx squared over L. Does it have the right units for a force? It's kilograms meters squared per second squared divided by meters, which makes it kilograms meters per second squared. It's good to know those are the right units. Those are the units of a Newton. So that's the average force for one particle. Now, I want to have a whole bunch of particles because I have a gas with n particles. So if I have 2 particles, what's going to happen to the average force? It's going to double. And if I have 3, it's going to, right, so it's going to go proportional to n. So if I have n particles, I'm going to have, and I'm just going to put force average now, is equal to the number of particles times this. So that's my average force for having a bunch of particles. How does that relate to pressure? Well, pressure is a simple function. Pressure is equal to force over area. So the average pressure there's my force, divide the whole thing by A. Well, that's simply A times L. That is the area of this surface here multiplied by the length. For my nice little box, what is the area of the end times the length? Volume. Now this, of course, is not a rigorous proof because this is only for a rectangular box, but it turns out that it is correct that this thing on the bottom is the volume. Now, this seems like I'm getting to the end, except for one thing's missing. That speed is the speed in the x direction. What about the speed in the y direction, the speed in the z direction, or just the stinking speed? Well, we have two relationships that we use to substitute that out. We have the Pythagorean theorem that says v squared is equal to vx squared plus vy squared plus vz squared. I said Pythagorean theorem, and I have one too many terms because that's the three-dimensional equivalent to it. So the one thing I should have done that I did not do. I should have, because of the average here, this really should be, we put it like this. This means average of whatever is inside the brackets. I forgot to do that. The average force is going to be the average speed in the x direction squared, or the average of the speed in the x direction squared. And so I should have those everywhere I have this. Okay, that was a mistake to forget that. So the speed squared is equal to speed in the x direction squared plus speed in the y direction squared plus speed in the z direction squared. Well, if I take the average, it'll just be like, The average speed squared is the average speed in the x direction squared plus the average speed in the y direction squared plus the average speed in the z direction squared. And the second condition is, if you have gas molecules bouncing around, how is the speed in the x direction squared going to relate to the speed in the y direction squared? They're going to have to be the same, because the x, y, and z are just arbitrary perpendicular directions. If you have just a completely randomized motion, any direction is going to have the same measurement for the average speed. So if you put these three together, or these two together, then the average speed, the average squared speed, v squared average, is equal to 3 times the average of the squared speed in the x direction. So I can substitute here to get rid of the x, it's 1/3. So here I have my result from this. Pressure times volume is equal to 1/3. Well, I'm going to put PV over N is equal to 1/3 mv squared average. Now, if it's an ideal gas, then what is PV over N equal to? Well, KT, because it's capital N. So what we have now is temperature is proportional to this 1/3 mv squared. Really kind of the final step. Kinetic energy is 1/2 mv squared, right? So average kinetic energy, if the masses are all the same, is 1/2 m times the average speed squared. So that means that m times the average of speed squared is 2 times the kinetic energy. And so this is so temperature is equal to, well, let's do it the other way. Kinetic energy average is equal to 3/2 kT. there's the outcome I was looking for. Something that tells me, yes, measuring the temperature is telling me about the average kinetic energy for what special case? If it's an ideal gas. If it's an ideal gas, then temperature is telling me what the average kinetic energy is exactly, right? I just take the temperature and multiply it by 3/2 K, and that tells me the average kinetic energy of the molecules. So you can see here's where we ended. My next slide. The important outcome, now you have a reason, you've seen the physics steps that you should understand. You understand the relationship between change in momentum and force. You understand the relationship between distance, speed, and time. You understand the ideal gas law. Putting those ideas together, we're able to show that temperature in ideal gas tells us what the average kinetic energy is. Now comes something kind of interesting. We get from the temperature the average kinetic energy. Kinetic energy 1/2 mv squared. One would think that I could calculate the average speed from that. But the problem is the square root of the average of the squares is not equal to the average of the originals. I will just give you a quick example to make sure people understand what I meant. Let's say we have 3 molecules, speed, and the number. V is so molecule number 1 has a speed of 1 meter per second. Those are our speeds. What's the average speed of 1, 2, and 3? You do 1 plus 2 plus 3 divided by 3. 6 divided by 3 is 2. So the average speed of those 3 is 2. Now let's do the speed squared. One squared is 1, 2 squared is 4, 3 squared is 9. The average of 1, 4, and 9, you add those together, and that's 14. 14 divided by 3 is going to be 4 2/3. Well, let's just put 14 over 3. I don't know. You can put it in your calculator and get a decimal number. It's going to be what? 2.67. Or, excuse me. Yes, 4.67. And now let's compare these. The speed average squared is equal to 4, right? 2 squared is 4. And 4 is not equal to 14/3. So the average of the squared speeds is not equal to the square of the average speed. Why not? Well, if you're doing averages, the first time we had an even weighting factor. Each one was weighted by 1. 1 times 1 plus 1 times 2 plus 1 times 3. In the second case, each one was weighted by its speed. So it was 1 times 1, 2 for the weighting factor, times 2 for the speed, 3 times the weighting factor, times 3 for the speed. The higher the speed, the higher the weighting in the calculation. And so it always turns out that the squares, the average of the squares is bigger than the square of the average. Now what we have in this equation is the average of the squares. If I square root it, I will have units of speed, but it's not the average speed. So we call it the RMS speed. That means the root mean square. The process of finding the root mean squared is you take the values, you square them. So you do the last thing first, you squared them all. Then you do the middle thing, you take the average, the mean. And then the last thing to do is to square root it. So VRMS here would be equal to the square root of 14 over 3. What is the square root of 14 over 3? I'll race you. I'm sure I'll lose. 2.16. By the way, I don't know why there's a 1 that showed up there. 2.16 meters per second is what you get for the RMS speed, whereas the average speed is 2. So the RMS speed, it's important to understand that there is a difference. It's not the same. The RMS speed is always higher than the average speed. But we can find the RMS speed from our work here. So we can determine from the temperature what the RMS speed is if it's an ideal gas. If we look at this equation and we relate this to this, that is 1/2 m v squared average is equal to 3/2 kT. Multiply both sides by 2 over m. And you get if I want to find the RMS speed, I have to square root. So VRMS is equal to square root of that, which is the square root of 3 kT over m. Now I have to ask one final question. What is m in that final equation I made? The RMS is square root of 3 kT over m. It's the mass of one molecule. It's not the mass of a mole of molecules, it's the mass of one molecule. So if you know the temperature and you know the mass of the molecule, you can just put it in here and you can get the RMS speed for those molecules. You know what I like more than the RMS speed? The average speed. It just makes more sense to me. And so James Clerk Maxwell, well, I guess this comes after the first clicker question. Which kind of energy is proportional to the temperature in an ideal gas? Okay, people were missing. Noah, James, Brandon. Okay. Our answers were 3, 16, and 3. Now, I am not going to have you discuss or re-poll this, especially because re-polling seems to be completely broken. Makes me sad. The correct answer, only 3 people had right. And I did not make a big deal out of it. I had the words on the slides, but the average kinetic energy, the temperature was proportional to 1/2 mv squared, right? Now we've learned 2 different types of kinetic energy equations. One was 1/2 mv squared, the first one that we talked about, and at that point it was the only one. And then we learned about 1/2 I omega squared. That's the rotational, which I don't even have listed here. Kinetic energy, and this is the translational kinetic energy. So we use this one. So the correct answer was translational kinetic energy. Why didn't we talk about the total kinetic energy? Well, we were treating the molecules as simple points. Simple points don't rotate. In reality, if you have a diatomic molecule, it does rotate. And so we're going to see some some additions to keep that in mind later. Okay, now to Maxwell. Maxwell and Boltzmann did statistical calculations for the collisions of atoms. If you have a whole bunch of atoms in a gas, and they came up with this equation that says PR is the probability of having speed V for a given atom or molecule in an ideal gas is given by this equation that has to do with temperature, the mass of the molecules, and the speed of the molecules. So for a given mass of a molecule, the distribution will change as the temperature changes. So at a high temperature, the speeds are understandably faster. At a low temperature, the speeds are slower. And this distribution has an RMS speed that you can calculate. Guess what we're going to do in class next Tuesday? We're going to take this equation, that's the calculus class, and we are going to work with it so we can find these different values. So the RMS speed turns out to be square root of 3/2 of the most probable speed. Most probable is if I take measurements, the most probable speed, the one that the most atoms will have. But then we also have the V average, square root of 4/pi times that most probable speed. And of course, the V most probable turns out to be also a fairly simple calculation from temperature. So we can calculate based on the Maxwell Boltzmann distribution the relationship. So if you know the RMS speed, you can immediately calculate what the average speed is if it's an ideal gas. Good to know, right? Here's something else that's interesting. Many of you have taken chemistry classes and you've learned about things like activation energies, right? Okay, you don't need to say anything, Peter. You either, Eric. What is an activation energy? Okay, it's the energy necessary to start a reaction. You have essentially a potential energy barrier. You have to get past that barrier, so the activation energy is the height of that potential energy barrier. Now we have a simpler kind of idea here with a fluid if we want it to go from a liquid to a gas state. In the liquid state, the molecules are all held together with a force, and you have to have a certain energy to break free of the rest of the molecules. And so we actually call that, well, it's energy, the latent heat energy, actually. I don't remember the name for it. But you have to have a certain energy for a molecule to leave to vaporize. And so, since the temperature is telling us about the energies, the speed here tells us about the energies, we can look and say if I have a distribution that is, some gas, or some, in this case, liquid, and it takes this much, that's a vertical line, perfect vertical line. It takes this much speed to have the right kinetic energy to break free. If I am at temperature 1, it's a very small fraction of the atoms that have a speed above that. So not many atoms, when they reach the surface, have a high enough speed, a high enough kinetic energy to break free. But if I go to temperature 2, where the most probable and the average, those speeds are below what's necessary to evaporate, what's necessary for it to break away, but I still have a very large percentage of atoms here that when they get to the surface, they will have enough energy to break away. So that means the number of atoms that leave my material per second is going to be much higher at temperature 2, even though I'm well below the boiling temperature. So the higher the temperature, the more evaporation you're going to have. We often think, oh, nothing happens until we reach boiling temperature. No, it evaporates. Which molecules are evaporating? Are they the ones with the highest speed or the lowest speed? Highest speed. So what happens to the average speed when you lose your highest speed molecules? They decrease. Well, in terms of temperature, what does that mean? The temperature decreases. So you probably heard of the term evaporative cooling. And you probably know that even on a hot day, if somebody sprinkles you with water and there's a little bit of breeze, you get cool. It's because of that evaporative cooling. You have the water on your skin, you have the hottest molecules of that water leave, and then your skin has something cold on it, and you feel cold. This works in dry climates. You can make what they call a swamp cooler. A swamp cooler, you just basically put a little water on some tubes. The water on those tubes evaporates, making the water cooler, and you have air flowing inside those tubes that then gets cold because you cooled the outside of the tubes. It works really well in a dry climate. If it's a wet climate, it doesn't work well at all because you have molecules that come and hit the water, they condense, they join the water, right? If you have a water molecule in the air, it comes and hits the water, it joins the water. And if you have a humid climate, you have a lot of water in the air, which means you have a lot more water coming in, and it makes it so the amount of energy increase from the coming in will balance the energy decrease by going out. So swamp coolers only work in dry areas. So here in Lincoln, where it's fairly humid during the summer, swamp coolers are a bad idea. If you go to Arizona, where it's pretty dry, it'll be 110 degrees, but it's a dry heat, the swamp coolers are great. Okay, another clicker question. How does the average speed compare to the RMS speed in a gas? Okay, James and Eric. Down to you, James. Okay, 3, 5, 12, and 2. So the majority, 12 out of 22, said the average speed is slower than the RMS speed, and the majority is correct. We go back to this graph. The RMS speed is here. The average speed is not shown, but you notice 1.22, V most probable 1.13. So V average is about there. All right, here was my actual slide on evaporation. If you have a container that is open to the air and the humidity is not high, then you have molecules that on average more leave than come in, and you have the evaporative cooling I talked about. If you close the container, you will reach equilibrium between the molecules coming in and going out, and then you won't have any net heating or cooling. Now, how do you know if you're going to be at equilibrium or not? Here's something that I have accidentally done in Lincoln. I have a cup of water and I go on vacation for a month and I come back and the water is still in the cup. That means it was reasonably high humidity. That never happened to me when I was home. And that would only happen during the summertime here. During the Christmas time, it would go right down because humidity varies a lot here. Now some diagrams you may have seen. Pressure volume diagrams. A pressure volume diagram is made by taking a material, that's this cyan color material, putting it in something that you can compress it, and then putting that whole thing in a temperature reservoir. So you put something like, let's say you put it in ice water. Ice water, that's a coexisting of ice and water. If it's pure water and pure ice, that will stay at 0 degrees Celsius. So you're keeping the temperature constant if, well, we haven't gotten to heat technically. That's what I'm going to talk about in just a moment. But if heat flows out, well, yeah, we've talked about heat, not all three. If heat flows out, that's what's necessary to keep temperature constant. It's going to flow out. And by doing that for a single temperature, you can see what happens as you compress it. And you have the liquid range, anything inside of this is a liquid. If you have the nice smooth curve, like this curve here, that's behaving like an ideal gas. But when you get close to the condition where you're going to have condensation, then it behaves not like an ideal gas, like a real gas. You guys may have heard of Van der Waals gases, or you might call them Van der Waals gases, because we're America and we pronounce our W's whoop, right? Even though that's not how he would have pronounced it. So the behavior, the shape of this curve, you need to use something more realistic like the Van der Waals equation to get the correct shape for those. These are just, this is a zooming in of the region where it condensed. So what's the point of this? So you can see as you compress, that has decreased the volume, the pressure goes up. And if it's an ideal gas, PV equals nRT. For constant temperature, P is inversely proportional to V. That was Boyle's law, after all. So for the ideal gas, when it's not close to the condition of condensing, you get that behavior. Phase diagrams are something that I am much more comfortable with. A phase diagram is plotting pressure versus temperature. And one of the things that's very cool about phase diagrams is this critical point. The critical point is a specific temperature and pressure above which there is no differentiation between a liquid and a gas. Now that seems unimaginable to us because I have water in the liquid phase. I bring my hand down when it hits that phase. I have that surface. I have the splash. I have steam, that's water in a gas phase, assuming I avoid all scalding things. You know, I wave my hand through it and I don't feel any special thing as far as the surface. But if you get to a temperature above 374 degrees Celsius or pressure above 218 atmospheres, you can't have a distinguishing between a liquid and a gas. Now, what's cool about this is that means that you can start with a gas here, you heat it up, then you pressurize it, then you cool it, then you lower the pressure, and you're almost the same pressure and temperature, but you went from a gas to a liquid. But never at any time do you say, ooh, it changed phase. Which kind of makes it a little confusing when we had those common phases and we had solid and or liquid and gas. It can change from liquid to gas and never change. Now, have I ever seen this done? No, I haven't. Have I ever been to the example I give in class? No. But if you were to go up to Jupiter and you fell into Jupiter, of course, obviously you'd die, right? Avoiding that idea, you start and it's a really, really thin gas, and as you go down, it gets thicker and thicker and thicker, until at some point you say, wow, this is really a liquid. But at no point would you have splashed, at no point would you said, oh, it just changed from gas to a liquid. It just would slowly get thicker because you are outside of the range where there is a noticeable difference between the liquid and gas phases. Now, another thing to point out on this, so critical point, highest temperature and pressure where you can have a differentiation between a liquid and a gas. Triple point is a specific temperature and pressure where all three of the common phases, liquid, solid, and gas, coexist. It's only a specific temperature if you have pure water. And so that's why the Celsius scale is no longer a centigrade scale. Instead of using an ice-water mixture for 0 degrees Celsius, they use the triple point of water, which is 0.01 degrees Celsius for the calibration point. Why? Because it's more easily reproduced. Exactly. So that's what the triple point is. And you can watch plenty of videos. I've tried to do the triple point experiment, and it's never worked out for me. Notice you can have a transition between a solid and a liquid. That would be melting or freezing. You can have a transition between a solid and a gas. That would be sublimation, going from solid to gas. And I never can remember the term for going from gas to solid. Does anyone remember that term? No. And of course, we can go from liquid to vapor. That would be evaporation or condensation. There is, those are the transitions that you can make. Water is different from carbon dioxide in that the slope of that line between the liquid and gas phases for water is initially sloped to the left. For carbon dioxide, it's initially sloped to the right. What difference does that make? Well, let's say we have ice at 5 degrees Celsius. Not 5 degrees, minus 5 degrees Celsius. We have ice at minus 5 degrees Celsius. So our temperature is, come on, zoom in. Our temperature is right here. And I step on it, well, actually minus 5 degrees Celsius. Since this is 0 degrees Celsius right there, it must be something like this. Okay, trying to do my best. If I step on that ice with a skate, what happens to the pressure under the skate? It increases because I have my force, which it turns out is a pretty large force, on a very small area. So the pressure goes shooting up. And what's going to happen to the phase if the pressure goes shooting up if I'm minus 5 degrees Celsius? It's going to go from a solid up. And what does it become as the pressure goes up? A liquid. So with the ice skate, if I'm on the ice skate, the pressure can melt the ice. Now, we use this all the time in physics class as an example of this process. Unfortunately, there is also the effect of the blade is a little warmer and the blade contacts the ice and also melts because of that. So it's not purely, oh, you compressed it and it melted. But when somebody's ice skating, you can see the little water, it's nice and shiny, in the track they left. And of course, if it gets cold, now I'm from California, from the coast of California, because we have plenty of cold places in California. Ice skating was not part of my childhood. But for many of you, it probably is. You got people from Minnesota? No? Wow. Usually we do. Well, what do you do ice skating when it gets really, really cold? When it gets really, really cold, you don't. Because when it gets really cold, you don't melt the ice when you try to skate. And then your skate just sticks to the ice and you don't go smoothly along. Or so I'm told. Because, like I said, it's outside of my experience range.